So, should we start? Okay, at least let's introduce. So, welcome everyone. Today we have Khyathi, who is from, I think she recently graduated from Carnegie Mellon University, and now she is a research scientist at Facebook Meta AI. And she is interested in, I think, controllable generation and multimodality. So, I don't know much about this topic, so I will just go through the bio. The avid goal of her research is to enable seamless communication between human and machine with multiple modalities and language. So basically, she's trying to bridge the gap between model prediction and humans, with especially around multimodality and various languages. She has also worked on vision and language generation, and basically adopting to content structure and persona, and particularly in long form text generation. Also, previously, she has worked on code switches and biomedical text. So there's a wide variety of topics she has touched over, I think, 5-6 years. Apart from that, there are a few achievements which are Rising Star ECS 2020 won the 6th edition of Bio ASQ Challenge. She is also very active in a Star CL conferences. I see her organizing lots of workshop as well as diversity initiatives in CL conferences. And she's also part of, I think, Widening in NLP workshop, which is about diversity and inclusion. And she has been on Dean Merit List and awarded Best Founder Student in her undergrads. And she's also very active in blogging, especially about machine learning at CMU. And in her free time, she love designing creative content. So yeah, this is a very lot of things in the bio. Probably I won't have that even after 10 years, but that's interesting. So before wasting any time, I would hand over to Khyathi. So today she will be talking about anchoring multimodal narrative generation. So it's about the generation work she's trying to do, particularly incorporating multimodality. And I hand over to Khyathi. So just people who have joined late, I just want to tell, so Khyathi got COVID and probably can't speak much. So there is a pre-recorded video, so which will be played about the talk, and then we can have questions after that. So hand over to you, Khyathi.
Yeah, thank you, Vivek. I just want to check if my screen is being displayed.
Yes, yes, screen is displayed. Yes.
Okay. Just start playing the video. Please feel free to ask any questions in between or at the end.
Hi everyone, I'm Dr. Khyathi Chandu. I'm a research scientist at Meta AI. I'm very glad to give this talk here today. Welcome to my talk on anchoring multimodal narrative generation. This is work done at Carnegie Mellon University as a PhD student.
Interacting with multiple modalities has seen a steep rise in both research as well as end-user applications in the past decade. Particularly, the interactions between vision and text has several socially relevant use cases such as image captioning, visual question answering, navigational instructions, visual common sense reasoning, etc. Despite the community efforts in these areas, there are still some standing problems. This motivates our research problem. First, let's look at this image. When the caption says a woman talking on a cell phone while sitting on a bench, the decoder or the model hallucinated the object bench while it is not visible in the image. Despite not fully capturing the image relevance, CIDER score is higher for the first caption compared to the second that does not talk about bench. Second, the images convey different meanings when embedded in different contexts. For example, the same image in the context of these left and right images seems to indicate other contexts, like a group of people gathered for a barbecue. The woman is trying to call her friends to find them, and they have finally met each other. The context in narratives is an important aspect to consider when understanding an image. When we want to generate different forms of text for the same image, we rely heavily on paired data with each of the forms and the image and train them as separate models for each of them, like the ones shown in the image. The image is still the same here, so having a controllable knob to adjust the forms T1 and T2 for the same image saves us from retraining the entire model from scratch. Finally, models often make simple mistakes like referring to the person as he because of the bias in the data sets. This is very easy to correct for the humans. So having a human interpretable intermediate representation helps give a handle for the intermediate corrections like this. So our talk is mainly focused on addressing some of these problems in the context of multimodal narratives. We have always been enveloped by narratives. Even if I want to tell someone how my experience giving this talk was, I'm going to give a long narration of this experience. Here is a quick peek into the past of how narratives evolved in a fun way. Let it be cavemen telling stories via shadows around fire, cave paintings, puppet shows, to more contemporary media, including movies, news, Instagram stories, etc. The ability to perceive and express a set of related content is fundamentally a human attribute. With the advent of virtual beings like Alexa, Facebook Portal, Google Assistant, etc., coexisting and sharing this ecosystem with us, it is time to teach them this skill. As we can see, there are two primary aspects to this problem. One is multimodality and the second is text generation. Why do we want to care about multimodality? Well, humans inherently learn from multiple modalities and multiple perspectives that they gain from these modalities. So the expectations from contemporary and 21st century technology like latest virtual assistants, etc., are a testimony for evolving ways to model these multimodal contexts appropriately. The main contribution here is the evolving ways to model these narrative properties from one modality and impose them to another. For instance, in this talk, I'm going to talk about narrative properties learned from text to improve visual narratives. Coming to text generation, it plays a pivotal role in communicating these contexts in human understandable languages. There has been a lot of studies, a study in single sentence generation. The main contribution in this lot is improving the naturalness in multi-sentence narratives that span beyond a single sentence, such as stories and procedures. This talk brings together both of these transformative technologies of multimodality and text generation to make a stride towards a long-standing and an elusive dream of human-like multimodal narrative generation in the form of stories and procedures. Simplifying this elusive dream to more manageable and achievable targets, we need to understand the properties that make narratives more human. What are these properties? Let's take the example of the sequence of images here. One of the appropriate story for this sequence of images shown on the left talks about how they went to the beach, the kids having fun, there being a lot of palm trees and staying in a resort. In a nutshell, we want to talk about relevant words that make up the story, which we call a skeleton. In this case, these skeleton words are composed of related words like beach, kids, palm trees, etc. This accumulates to our first narrative property, content, which contributes to the relevance of the images and the generated text. Formally, it is defined as the quality of being closely connected, appropriate, and informative. Next, moving on to the property of structure. Consider an example of a sequence of images of making a delicious cheese garlic bread. You want your bot to now explain the stages step by step. The step-by-step process in the recipe is depicted in the text on the right side. You first talk about 25 to 30 centimeter of baguette, half cup of softened butter, etc. And then mixing these ingredients, followed by step 3 of mixing it onto the bread. And finally, in step 4, to serve very nice and hot. There is an inherent structure to represent this information in an orderly fashion. This is particularly important in long forms of text that are made up of multiple sentences. For instance, it is coherent to talk about the recipe in the order shown on the right, but it is not a coherently ordered recipe if you talk about garnishing first, then mixing, followed by listing ingredients at this point and preheating at the end. You might have all the information that you need in there, but not in the right order, which inhibits the understanding of an entire narrative input. This brings us to the second narrative property, which is the structure contributing to coherence. Formally, it is defined as the quality of being logical and consistent. There we have content and structure. Now let's look at the same set of images we saw first. Each of us would express this story in different tones or realizations based on individual personalities. Let's take a couple of example personalities, like how a bot would personify as Gandalf the Grey and Iron Man and contextualize the story. Gandalf would say something like, "Midsummer is a beautiful time for Lake Town. The young humans walked along the shore bravely. One must experience the depths of the pool. And yes, I'm here and you're lucky to be here too." Notice the bolded words that give a sense of how they represent Gandalf's tone. Now, moving on, Iron Man would express the same set of images as something like, Pepper and I went to a beach holiday. No tech and even evil villains invited. I get to make the invitations and I own the island. Notice the difference in the choice of words. The first is clearly a wise and old school way of expressing. The second has colloquial usage of terms like tech and stuff in his universe. You can see that he's bragging about his riches. Some ways to capture these idiosyncratic realizations are incorporating the personality in generation or expressing the same content in mixed languages. That is, maybe by switching multiple languages where these languages interact within the same utterance, like code switching. Contributing to different ways of expressing this same content in the form of personalities or these mixed languages. This brings us to the third property of surface forms contributing to the expression. And formally, this is defined as choosing the surface tokens derived from the underlying representation. So here are the three properties: content, structure, and surface forms that are key to making narratives more human-like. These together construct what we call multimodal narrative intelligence. Like even for this talk, I first ingested different portions or segments of my paper, planned my content first, how to organize my talk, that is the order and my style of presentation of the talk. So during my PhD, I've tackled all three of these methodological directions, primarily ranging between visual and textual modalities. In addition to the individual contributions to this overarching theme, I have also worked on surveying the task-agnostic techniques in neural text generation, and also an opinion piece on identifying the important yet missing elements of contemporary research in grounding. So during this talk, I'm going to focus on only three of them. I'll mainly focus on the content part and briefly on improving structure. Finally, I'm going to very briefly bring forth the missing portions of grounding tasks and techniques in contemporary research, which is our recent ACL 2021 paper, where I provide category-wise recommendations on how to adapt current techniques to drive the future in research on grounding. Before going to the specifics of each work, I'll first take a step back and present an underlying modeling ideology of grounding these narrative properties via what we call a skeleton framework. So what are these skeletons? A skeleton is a supporting framework, basic structure, or a condensed essential part of something. These skeletons can be derived from both visual modality in the forms of scene graphs or text. We will look at skeletons derived from text for each property that we discussed before. We'll use a similar skeleton framework to provide guidance on each narrative property for each sentence. Our input is some stuff from visual modality, either an image or a sequence of images, and a skeleton from which we generate a narrative. There are several advantages of using the skeleton framework. The first is obviously the contribution to improving the overall narrative generation. The second is that these skeletons give a better handle of controllability of the generation. Next, because they in the forms of, let's say, entities, etc., they are human interpretable intermediate representations that can help understand the model generation, which for the same reason also gives us a handle into the semi-automatic human in the loop corrections. We will see some of them in detail in this talk. So how do we get these skeletons? For more explicit skeletons, we present two routes. The first is training a weakly supervised skeleton prediction model that is either trained on vast amounts of external data or from the training data, or more straightly using off-the-shelf tools to get weak labels to derive a loosely defined skeleton. Implicit skeletons are derived from the surrounding example-based context alone. With the input images I and the output text T, there are different ways for these modalities to interact with the skeletons S and the predicted skeleton S dash in the text. The first category is independent modeling, where the visual modality I and the skeleton modality do not interact at the encoding level. We can have a simple baseline of I going to T or multitasking with an auxiliary prediction of the skeleton and using the predicted skeleton to hierarchically multitask for text generation. The next category is simple fusion of both images and skeletons that can be done in the forms of both early and late fusions. There are the same variants as before with single and multitasking here. The last category is latent modeling, where the latent representation is attained by fusing a latent representation of single modality or selective cross-attention across modalities. With all the fundamentals about the models clearly laid down, we can now easily navigate through each component. So first, let's begin with content. Let us look at the task of using entity skeletons to denoise content. Why is this important? For example, consider this image. It is not at all uncommon to see an alt-text caption like apartment for sale on the internet. This kind of data is uncharted and is more accessible on the internet without the effort of any manual annotations. Moreover, getting rich annotated captions is very expensive. Even if we do get these annotations, scaling it to multiple languages is really hard. A potential solution resource to this is leveraging the vast uncurated web or internet text derived from the alt text captions, which can be noisy. So we propose to introduce content skeletons and break down the end-to-end models to two simpler and more controllable tasks. As a byproduct, the intermediate outcome is also interpretable to humans, allowing for human-in-the-loop corrections. Here is the overview of the baseline and our proposed approach. The baseline approach takes in the image and generates a caption. This generates a largely peripheral or irrelevant caption like custom posters for a wedding. This happens because the model has seen several such noisy instances in the training data. Well, when extending it to captioning in other languages like Hindi and Italian, these errors just keep compounding. To mitigate the problem of this unwanted noise, we introduce an intermediate task of skeleton prediction. This skeleton is in turn used to guide the captioning model. For example, in this instance, the predicted skeleton words are collection and book. These words are further used to generate a caption, collection of books on display. Using these relevant skeleton words in English helped us also generate cross-lingually appropriate captions in other languages as shown in the figure. This content skeleton-based generation is our proposed approach. So first, let's discuss how we get the skeletons via distance supervision. We have 4 types of skeletons to analyze and understand the contributions of different factors of the content listed here. First is iterative refinement. This means that all the caption words are used as skeletons. This is to understand whether subselecting words is important in denoising. Second is nouns and verbs, to understand if the content skeleton is important or not. Third is salient nouns and verbs, to understand whether truncating the skeleton words based on TF-IDF scores or any other priority scores is important. Finally, we wanted to verify the performance of much simpler skeletons to check if they further help in denoising. So we used just the nouns instead of nouns and verbs. Our first stage is the skeleton predicting stage. We extract the global features of the image using the graph race features extractor and we extract regional features using RPN, followed by a faster RCNN, followed by graph raise again. These global and regional features are then combined using a fully connected layer from which the query, key, and value are extracted for the visual part. These are then fed to the transformer encoder, which is then passed through a decoder to generate the caption. We perform beam search in the decoder with a beam size of 5. Once we predict the skeleton, we propose 3 ways to utilize them. First is skeleton encoding model. The skeleton words are subword tokenized and are initialized with BERT embeddings. This is passed through the textual encoder to encode the representation of skeletons. To improve a better interaction between the features from these different modalities, we performed an attention mechanism called text as side, where the key and the value for the textual part remain the same. And for the visual part, while the query comes from the visual features, the key and the value are a combined representation from both visual and textual modalities. This is done particularly to increase the influence of textual contribution and in specific to increase the contribution of the skeleton words in textual modality itself, as the end task is to generate text, which is the caption. The decoding process remains the same as discussed before. So this is the key encoding model. The text as side cross attention creates a latent representation from which the text is decoded. The second method is skeleton decoding. The skeleton and caption are concatenated and predicted by the same decoder. This is not a two-stage model, as the model is trained using both the skeleton and the caption in the same training example and used to predict both of them autoregressively. The model first predicts the skeleton words conditioned on the previously generated skeleton words, and then every token in the decoded caption attends to the entire predicted skeleton as well as the tokens of the caption decoded until that time step. There is no latent interaction between the modalities in the encoding stage. S dash, that is the predicted skeleton, is predicted first, from which it is further used to predict T, that is the caption. To bring both the above models together, we simultaneously encode and decode the predicted skeleton. This brings the benefits of bidirectional attention on the input features, image and predicted skeleton words, and autoregressive attention on the re-predicted skeleton words while generating the caption. The text as side cross-modal interaction produces a latent representation, which is then used to predict S double dash, which is further used to predict T. This concludes the models. We carry out our experiments and use the conceptual captions, multilingual conceptual captions for training. We use the T2 test set to perform automatic and human evaluations. I'm going to exclude the performance on automatic metrics. Please check our paper for more details. The test set contains 1,000 images, each rated by 3 distinct annotators. The interface is shown on the slide. While comparing 2 models side by side, they're randomly assigned A or B in the interface for each image to avoid any rater bias. We use a state-of-the-art baseline from Chandu et al. At the time. For relative rating, for each image, we ask the raters to choose the most relevant caption. Comparing caption A to caption B, raters can select relative options as shown in the third column. Wins are the percentage of images where at least 2 out of 3 annotators voted for caption generated with our approach, and losses are percentage of images where at least 2 out of 3 annotators voted for caption generated with IMG to cap or the baseline approach. We compute relative gains in this side-by-side relative evaluation as the difference between wins and losses. Here are the human evaluation results for model comparison. As we can see, the models that use subselected content skeletons, specifically nouns and verbs, all show positive gains over the baseline. This shows that subselecting content skeletons helps improving image captioning. The last column, corresponding to iterative refinement, does not subselect content words, and this fails in comparison to the baseline. Now coming back to the first 3 columns, skeleton encoding gives much higher gains than both skeleton autoencoding and skeleton decoding. Also note that skeleton autoencoding performs better than skeleton decoding. So we used the skeleton autoencoding model to cross-lingually transfer the predicted skeletons to guide the generated captions. As we can see, we have seen positive gains in 4 languages, French, Italian, German, and Hindi, while we see a minor drop in Spanish. The reasons for this are detailed in our paper. In order to further analyze where the gains are coming from, we analyze the captions based on multimodal discourse coherence. Alikhani et al. Proposed multimodal discourse coherence classes, some of which are shown on the slide with respect to this image. First, visible category that denotes visually recognizable aspects of the image. For example, in a caption, a man and a woman are cutting a wedding cake. Man, woman, and wedding cake are visually recognizable objects from the image. Second, meta category that provides meta-level details about how, when, where the image is captured. For example, a warm summer afternoon gives this meta information about this image in the caption. Third, story category provides us details on potentially non-visible context from the scene. For instance, there is no way that we would understand just from the image itself that the couple are celebrating their 5th anniversary. We try to understand why our models give better human evaluations based on these categories. Here is how the data categories change that affect the human evaluations change between the baseline and our model for each of these categories. The story-like captions reduced by a good 16%, which thereby contributed to a 10% improvement on human evaluations for these story-like captions. The same shift on data was about negative 7.7%, and this change in meta contributed towards a 13% raise in human evaluations. In the visible category, the human evaluations improved by 10% with a change of approximately only 5% of the data. So this is where we seem to likely get our improvements in human evaluations. More captions are now categorized as visible type, that is, captions that are visibly informative. This is therefore helping in reducing hallucinations or non-visible contexts. Next, we explore the effects of controllability of our model, starting with length. Controlling length is very important for applications that limit caption length due to UI restrictions. Here is a graph on how the number of skeleton words and the number of words in the caption are correlated. When the skeleton words are 2 and 3, the percentage of captions with larger lengths keep decreasing from left to right. As the number of skeleton words increases to 4 and 5, the same percentage of captions first increase as we go to the right and then start decreasing after a point. Even comparing between 4 and 5, the median length for 4 is lesser than that of 5. We discussed the controllability of length with more examples in the paper. Coming to guiding the content of the caption, here is an example of giving different skeleton words for 2 images. So when we give the word magic as the skeleton word, our model takes cue from this skeleton word and fills in the rest of the context from the image to generate the captions. The magic of the colors for the first image and the magic of the lakes for the second image. The words color and lakes are appropriate for the respective images. However, guiding with irrelevant skeleton words can also be detrimental to the caption as seen in the last column. While the words are relevant to the first image, they are not to the second. However, in both the cases, the captions are heavily influenced by these skeleton words. Finally, we show that skeletons give an interpretable handle to make human-in-the-loop corrections. We show that in the case of gender debiasing of captions, end-to-end models make embarrassing mistakes while generating gender-related text aspects. There can be non-trivial sublexical gender dependencies in other languages, especially non-Anglic languages. Skeleton correction is a more robust way to handle biases as opposed to caption post-processing. So when we changed the skeleton word man to person, the final generated captions have 46% less mentions of the word man. With the same correction of changing English skeleton word man to English skeleton word person, we observed a drop of 70% of mentions of the word admi, which were replaced by VIPT in the final captions, which were equivalents of man and person respectively. There we go. We have a human interpretable intermediate representation that can be used for human in the loop corrections. Now, if there is one picture like on the slide, this is the task of image captioning that we have just seen. Independently, this conveys something like a man swimming. But the same image, when given with the following left and right set of images, gives us the sense of a holiday where a man went to the beach during the day, followed by a mountain hike in the night. So our goal now is to use the overall context implicitly to bridge the content. For instance, when we are presented with a missing image amidst a sequence of images, we can almost easily approximate the corresponding textual description for it. The same is not easy for the machines trained with regular seek-to-seek training procedures. This leads us to the main challenge of machines not being able to infer missing context, which is a fundamental incongruity between how humans and machines learn. We address this ability to learn from missing context by implicitly using the surrounding context through infilling. We introduce visual procedure telling or VIPT dataset that is similar in spirit to visual storytelling. It includes 10 domains of procedures with stronger interleaved context between adjacent sentences. In total, our dataset includes 46,000 procedures and about 340,000 image text pairs. In the interest of time, I'm going to skip over the details of the dataset. Coming to its aspects, it is more challenging long-form generation task because, as we can see, the average number of steps in VIPT is higher than VIST. Similarly, the average number of words per step in VIPT is also much higher than VIST. More importantly, it is not just the length, but also the overlap between the words in such long lengths. For this, we compared the diversity in vocabulary for each step by computing the average percentage of unique words in a step with respect to the rest of the narrative. The diversity in surrounding context is only 39% in VIPT, which means that there is a lot of token sharing in the context compared to a high 60% in VIST. These strong overlapping contexts motivates the idea of learning via bridging the surrounding context, making it an effective testbed for learning with interpolation or infilling technique. This makes it a simple yet very effective technique for overlapping contexts. Our general seek-to-seek model takes in a sequence of images, extracts visual features, passes them through a narrative context layer with GRUs or transformers, combines the local and narrative level global contexts, and finally decodes each sentence step by step. We now add the missing step prediction objective to this underlying seek-to-seek model. The local context or the image-specific features are masked with an infilling indicator function. An infilling index INIDX is randomly sampled. The local features for INIDX are all masked to a zero tensor while not affecting the rest of the local features. The model employs cross-entropy loss to reconstruct this missing context. In this way, the model is encouraged to learn missing local context from surrounding context. An extension to this is scheduling rates of these missing contexts. For the first quarter of training steps, 0 local contexts are infilled. For the second quarter of the training steps, this is increased to 1. And this is finally increased to 2 for the last 2 quarters of the training steps. Coming to the results, infilling can be applied at train time and during inference. When we apply infilling during train time, here are the results for Blue 1 to 4, Meteor, and Rouge. As we can see on the procedures data, our V-Infill model improves the scores on all metrics except Meteor, for which our V-Infill R shows a gain. The same trend is not observed in VIST dataset, and the scores along with the reasons are presented in our paper. Now coming to the infilling during inference. This is a very interesting use case because acquiring parallel data from the wild is often not feasible. By parallel here, I mean parallel between images and text. Instead, if our training model is able to bridge explicitly missing context during test time, when the corresponding image is absent, it can address real-world data imputation problems. In the interest of time, I'm not going to go into details of these numbers, but I would like to point an important observation here. With our V-Infill model, on an average, the scores tend to be higher when the infill index is towards the right as compared to the left, that is towards the end of the procedure as compared to the beginning of the procedure. We also performed human evaluations. The results indicate that our V-Infill model is preferred 64% of the time with 20 evaluators on 10 recipes. In the interest of time, I'm going to skip over other experiments and analysis. So the main contributions of using the skeletons are, of course, the direct improvement is seen in the generation quality, either in terms of automatic metrics or human evaluations. We showed how skeletons help in denoising large web scale data to improve image captioning models. We also show cross-lingual transferability of English skeletons to 5 other languages. Skeletons also helped generate more visually informative captions, and we also show the effectiveness of the intermediate content skeletons to control and also enable human-in-the-loop corrections. Instead of explicitly using the skeletons, we also explored the infilling technique that implicitly uses the surrounding context to effectively bridge the missing context with curriculum learning. We introduced a large-scale visual procedure telling dataset, and more importantly, our proposed model is robust to missing context at test time that can directly help us deal with missing information or potentially help us deal with generating larger explanation for a single step. A promising bet for future directions based on some initial experimentations is using skeletons for unpaired image captioning with no parallel image text annotations. While infilling model is robust to missing information, it sometimes generates very underspecified content. Using or predicting explicit skeletons in these cases might help reduce the underspecification problem or the hallucination problem. So coming back, we used entities and context as skeletons for content and saw the following advantages. So moving on to structure. The goal here is to use structure skeletons to improve coherence. This task emphasizes on instructional in-domain text that has clear transitions between high-level phases of the narrative in comparison to stories. To briefly recap, this is important because we want to talk about information in a particular order. That is, for example, we talk about ingredients first, cutting them next, mixing and serving at the end. We use a subset of the VIPT dataset here. How do we derive and represent the skeleton forms for structure? For this, we make use of clustering and finite state machines. Here, we have 2 sources of supervision. The first one is our dataset, which has both images and corresponding textual recipes. The second is the unsupervised dataset, which is a huge dump of the textual recipes without any images. These sentence embeddings are then passed through a clustering algorithm. Let's call these clusters phases in the recipe. This is the first form of structural skeleton representation. Next, we not only want the sequence of phases, but also the transition from one phase to another. Hence, we pass the phase sequences through a finite state machine. From this, we get the state sequences in hard form, which is the second skeleton form. We also get the soft representation of the state sequences from the transition probabilities between the states in the finite state machine, which is the third skeleton form. The boxed ones shown on the slide are the 3 skeleton forms for structure. Combining these structures in the model that we discussed before. The first is the baseline model, which we discussed in the previous section. This independently models I to decode text T. The next model, SSID or scaffolding structure in the decoder, makes use of the structure derived from the state and phase representations, directly concatenating it in the decoder. This skeleton can be any of the three forms discussed earlier. We are thereby constructing a latent representation of the structure skeleton and fusing it with the visual modality. Next, we go one step further in our SSIL or scaffolding structure in the loss model, where we pass the decoded steps through the clustering algorithm to get the phase sequences followed by the FSM to get state sequences. The idea is to measure the divergence between the phase sequences of the ground truth recipe steps and the generated recipe steps. This deviation is measured as KL divergence between these phase sequences. Here, we are performing hierarchical multitasking that predicts the skeletons from the text. The first task is to decode each step in the recipe, which uses a cross-entropy criterion L1. And the second task uses KL divergence between phase sequences of the decoded and the original steps to penalize the model, say L2. We perform grid search over the number of phases, which is the number of clusters, and the number of states, which is the complexity of FSM, both of which are hyperparameters. States and phases of 140 seems to perform good, and we use this setting for our further experimentation. We observe that SSIL model outperforms the rest of the models in terms of automatic metric meteor. Similar trends are observed in Blue and Rugel, which are detailed in the document. Firstly, our models are taking into account the contextual nature of the narratives. We observe that with our baseline and SSID model, incorrect structure with respect to the images are generated. The first step introduces that it is simple and delicious recipe. And the second step is usually listing ingredients. However, we are able to control the structure better with our SSIL model, where for this example, the model appropriately generates ingredients in the first step and mixing the ingredients in the second step. The baseline model also hallucinates the content about grill for the last image. This is rectified with our SSIL model. We also conducted human evaluations in the form of preference testing. Each of the participants was asked the following two questions: preference for the overall recipe and preference for structurally coherent recipe. Our SSIL model was preferred 61% and 72.5% for overall and structural preferences respectively. That brings us to the conclusion of structure. The main contributions here are the following. Structure is a construct that is very hard to define. We showed unsupervised ways to learn structure skeletons from external data and demonstrated using them in the forms of state and phase sequences. In this way, we were able to incorporate schema into procedural text so that a global context is maintained. Enforcing a structure inherently helped reduce repetition of commonly occurring phrases like ingredients, etc. We believe that a prospective future direction here is to use gradient backproppable scaffolds instead of FST that can both jointly learn and represent structure. In the interest of time, I'm not going to cover the surface forms in detail, but to briefly recollect, our techniques model how to induce distinct personalities or characteristics such as Gandalf the Grey and Iron Man to visual storytelling. So here I'm not going to go too much into the details. We have primarily experimented with multitasking and early and late fusion modeling categories as a summary. I'm going to briefly go over the main contributions in this section. Annotated personalities are not often available for all domains or data set through explicit annotations, though this is a crucial form of surface realization. So we used weak supervision to predict labels of condensed personas as skeletons for visual stories. I've not discussed altering language choices here, but that is yet another way to realize different surface forms that I'm very happy to discuss later. we show that the stories carry forward the same tone consistently, and we can have a control to change the persona in the inference time. Some of the prospective future directions as observed from the analysis are retaining linguistic priors in modality fusion to not affect the decoding or the underlying language model. Secondly, not all personalities suit the training data of the stories or specific instances, and sometimes the visual contexts themselves prime the tone of the story, and hence both of these need to be taken into account while creating the weekly supervised data. Well, all in all, these three components help us better ground the narratives to make them more human-like. Along with each of the components, we also discussed the incremental future steps. Well, is this enough to achieve our bigger goal of grounding in communication? Now, taking a step back to get a bigger picture, I would like to briefly go over some of my future ideas and prospectively some of the things I would like to work on. In the path ahead, I will now taking a step back to get a bigger picture. I would like to briefly go over some of my future ideas and prospectively some of the things that would enable grounding. NLP community have been studying grounding in a variety of contexts. For instance, we collectively worked on grounding in knowledge graphs, ontologies, emotions, and even in multiple modalities such as images, videos, and audios in addition to text. In NLP, we operate under the assumption that grounding is any kind of linking of text to data or other non-textual modality. For example, in this case, identifying that a group of pixels are mountains. I have been asking myself the question of whether this is really enough. Deriving inspiration from cognitive sciences, grounding is essentially the process of establishing mutual information collaboratively that is essential for two or more interlocutors to communicate successfully. Here, I present our investigation of the gap in these definitions and some actionable goals for future on how to bridge them. So our first question, the missing dimensions of grounding from our current NLP tasks. And I believe grounding interactively and in a conversation is a big chunk. After a thorough review of the literature of papers on grounding in the last 40 years, I believe these three dimensions of coordination, purviews, and constraints are very important to bridge this gap. We believe that these are some of the systemic dimensions to bring the current state of models closer to what is missing in grounding. Let us take a closer look at each of these dimensions more closely. Coming to the first dimension, which is coordination in grounding, traditionally in the linking sense, the sequence for this form of interaction includes the human querying the agent querying the data or knowledge it acquired, the agent retrieving and framing a response, and the agent delivering it to the human. In this setting, the common ground is the ground truth knowledge base or data. The human and the agent have common ground by assuming its universality without any external references. Therefore, successfully grounding the query relies solely on the agent being able to link the query to the data. In contrast, dynamic grounding posits that common ground is built via interactions and clarifications. This reflects human communication more naturally. The steps for establishing grounding is a part of the interaction that includes the human querying the agent requesting clarification or acknowledging, the human clarifying or confirming, and these steps loop until a common ground is established. And the remaining steps of querying the data, retrieving or framing a response, and delivering the response are same as that of static grounding. The process of successfully grounding the query not only relies on the ability of the agent to link the query, but also to construct the common ground from the mutually shared information with respect to the human. More concretely, here is an example. In static grounding, when you ask an agent, can you place the dragon fruit on the rack? The agent simply does it and replies done, provided it understood the instruction. Concretely manifesting dynamic grounding, there are primarily two ways to materialize this. First, with respect to language learning, what if the agent does not know what a dragon fruit is? The agent needs to first ask, what is a dragon fruit? Learn from both the language description of reddish pink fruit and the visual input to ask and learn what a dragon fruit is and use this knowledge later. The second is ambiguity resolution. When there are multiple racks, it is very natural for a human to ask the agent which rack to resolve ambiguity. We expect the same from the agent to ask a clarifying question to resolve ambiguity and then place it on the second rack or wherever appropriate. Some of the prospective methods that I would like to work on to address this include the following. First is human in the loop error correction. Humans influence the context with their actions. So humans and machines should work together to develop training data. I plan to look at this at the 3 stages, including data collection using adversarial samples, during training with reward score from humans, and third, during inference by adding satisfied responses to training data using continual learning. The second is iterative refinement, where I believe we can seek inspiration from theory of mind, which is promising to look at for iteratively or progressively asking and clarifying common ground. I strongly believe that immersive technologies like AR and VR can revolutionize the way we interact with artificial agents. AR provides opportunity to perform spatial references like absolute, relative, or landmark-based or disambiguate interactively based on properties. These clarifications can be offered explicitly, implicitly, or with a list of options. We are currently collecting a data set where humans interact with an environment to perform a task. So there is audio, text, and interactive conversation. Here is a snippet of the conversation and a sample video playing a conversation that we recorded that is transcribed on the slide.
So
next, moving on to our second dimension of purviews of grounding. The purviews of grounding in humans expand horizons stage by stage. We begin with localization, where we associate or link entities like Robert Downey Jr. to Tony Stark and Iron Man. Next, we ground these concepts to external knowledge. For example, here, when we want to know if Tony Stark is the head of the shield, we refer to external sources, including movies and the comics, to conclude that he is the head in only one of them. Upon learning about an entity, we also understand some common sense attributes such as Tony Stark is not a real person but is a character in Marvel. So any contract is not with Tony Stark but with Robert Downey Jr. who played the role. Finally, we adapt and personalize our responses to people very naturally. So if we have a conversation about Robert Downey Jr. and ask about a movie suggestion, knowing information that maybe I like Disney movies, I would like to contextually get Robert Downey Jr.'s Disney movie as a recommendation. I believe this calls upon an opportunity to reevaluate our benchmarking paradigm. Benchmarks have enabled make remarkable successes in research and model development. However, our current benchmarks collate multiple data sets with the same end task to evaluate generalization across them. In addition to this paradigm, we believe that a longitudinal style of benchmarking will expand the purviews to bring tasks closer to the real world scenarios. Here is an example for how this can be designed for a visual dialogue dataset. For the same dataset, we first have an object detection leaderboard, followed by knowledge graph-based response generation leaderboard, followed by visual common sense reasoning leaderboard, and finally empathetic response generation leaderboard. Intuitively, deriving motivation from neurosymbolic AI seems like a good bet here, with the logical interpretable compositionality that it offers. Anyway, having this bigger picture helps have a set of guiding principles before collecting our future data sets that can potentially increase the longevity of the task and the data set and bridge the gap between research data sets and real world applications. Finally, a third dimension on constraints of grounding is here. These constraints are primarily imposed by the medium of communication. Like we have been discussing throughout the talk, modality is an important medium affecting the nature of interaction. For example, when you and the agent are co-present in the same environment, utterances can include executable actions in the environment, like getting you the ball and disambiguating the ball based on person-centric or the agent-centric views. Certain communications only allow visibility, like in the cases of visual question answering, where both agent and the person talk about an image. Finally, audibility, where the medium constrains possible action spaces as compared to, for example, co-presence. In addition to modality, the way we give or take cues in an interaction are constrained by the media. Here is a table demonstrating the medium of communication in the rows, ranging from face-to-face to video conferencing to emails, that are analyzed with respect to modality and cues like cotemporality and revisability that each of these media offer. These are some of the missing dimensions that I believe will be effective in to address in achieving a more holistic sense of multimodal grounding. Finally, these are the different problems that we tackled through the talk. Finally, taking a step back for one last time, working on the grounding of narrative properties also has a broader impact on society. Improving on these properties is already becoming a stipulation for the advancing 21st century technology. There are several practical applications of generating narratives with near human capabilities by deriving from multimodal context. For example, informative bots that help assist in e-teaching, directions to a destination, or even collaborative authoring between machines and humans, like assisting in writing a novel or making a presentation, etc., demand pretty accurate content delivery. In addition, other applications include logical constraint-based neural decoding, like this work from AI2. Collaborative bots that help authorship of stories, comic strips, or interactive game building, or natural language instructions for web or mobile interfaces are required to follow cues and maintain a structure in addition to having appropriate content. Recently, there has also been a large surge in empathetic bots that are trained to care and react with a personality. Some growing ones in this include Choice from, of course, Microsoft, Lucy from Fable, Lil McWilla, who is an Instagram influencer, and animated celebrities from Superplastic, etc. Finally, recent advancements in virtual and immersive technology like Oculus, Microsoft HoloLens, Facebook Portal, etc., can benefit a lot from this multimodal narrative intelligence, where you need to be coherently able to speak multiple sentences naturally. Some other selected related projects that I worked on are dual-staged GAN with a continuous softmax to generate text in multiple languages at the same time, hierarchical entity modeling for visual storytelling, multitasking for language modeling, and mixed script instruction synthesizer. I'd love to discuss more about any of these if you're interested. So here I conclude my talk. And this is a summary of what all we have discussed today. Thank you so much for your time and attending this talk.
So we can extend for 5-6 minutes, and people have questions, then Khyathi can take questions. But it was wonderful talk. Thanks for this very detailed and like thorough and future work also. Like it's very detailed talk. Anyone? Any questions? Okay. So so the problem which you choose about storytelling is I think relatively very hard and challenging aspect. And as you realize, like they are more than just generating text. It need to be grounded. It need to have coherency. It need to have some controlled, all those aspects. So and also I feel like this also have applications kind of thing in robotics and like things which you also discuss some of this. So what's your thought on this aspect? Like what, where the things are there, hopes like is language generation can really do all these things? Like because currently the problem with language generation is kind of one is evaluation, which how we evaluate things, as well as the hallucination and the grounding in the facts thing. So what's your thought in that aspect?
Yeah, I think you're right. The When I began my PhD, generation was still not a topic that's reliable to work on. But towards the end of my PhD, GPT has come out and generation has become easier. But the challenges that still remain are having consistency and grounded to some factual knowledge bases, etc. And evaluating that is, like you mentioned, still very hard. So, like any other like any other advancement, I think when a popular open source model comes out, the fun applications first would be the creative ones, not uh, which are not going to risk any actual human lives, like doing it for medical or something. So storytelling as a creative part, even if it messes up, is still not going to be as unreliable compared to a lot of other applications. But as we move towards more responsible and reliable applications, such as maybe maybe reporting news stories, or giving medical reports to patients and generating them, etc., we need more grounded generation techniques that fit well with maybe tables or other kinds of knowledge sources. Vivek,
Sorry, well thought answer. Thanks. I have one more question. You briefly talk about multilingualities. So, do you think there anything need to be changed when we move from one language to another? Because the context things, it's not just the languages change, but also the things or the objects or people are referred also change across languages. Some are gender neutral, some are gender, like I'm just giving one example. So in that context also, do you thought like when we change storytelling in other languages, how things will differ, and do we need something more on that aspect also?
yeah, very apt question. Thank you. And you have worked a little bit on code switching too. So, like, um, I think for the current state where the models exist, which are multilingual, are still large scale multilingual, but not switching. That means they have some kind of embeddings or semantic space that projects different languages into a common projection, but do not have the ability to switch from one language to another, which can come with different cultural biases, or uh, how you are going to refer to a dignitary or a friend, the casualty that it comes from, etc., which all need more linguistic based structure enforced on the language models that we have.
Thanks. I want to delay more. Let's thank Khyathi. It was a very well thought and very good talk. I really enjoyed it. Thanks again, Khyathi, and thanks for giving this talk at this short notice and in this condition. Thank you for agreeing on this, and thanks everybody for attending this. See you next week. Thank you. Thanks all.
Thank you for having me. Bye.